Hi, everyone. My name is Mikhail, and I'm software engineer in Google anonymization team, and would like today to present Urania, a differentially private framework for gaining insights into AI use. This is a collaborative effort across many Google teams. We published an archive paper where you can find more in-depth details about the algorithm used. And let's start with the problem statement. There is a standard life cycle nowadays in the AI world where we deploy AI features, models, and then people use them, run inference. And ideally, we would like to learn from this interaction data. However, the main source for learning are raw unstructured logs. And we would like to learn from this data to improve the products, steer the roadmap, and maybe make the products more secure. But these raw unstructured logs, they are highly sensitive. They contain PI. Therefore, there is no human access allowed to access them. And also, we learned from the past that ad hoc solutions, such as, for example, LAMP sanitization, they have uncontrolled privacy risks. And this is privacy by hope, and we would like to have privacy by design. Therefore, we created Urania for this. Urania contains millions of raw unstructured logs and transform them into differentially private, safe summaries, trends, and insights about this data. This is a shift from privatizing not the input, but privatizing the aggregate insights. And Urania has formal epsilon delta differential privacy guarantees. The privacy unit in Urania is by default the one example, one row. However, if the data set has stable user identifiers associated with each row, then it can be user-level privacy achieved. And let me start with the web UI we created to give our clients a nicer way to consume the insights. We have a trend line to track the topic over time. There are predefined categories that users predefine beforehand, and then they can contain subcategories. You can see the trend line and their relative size among the data set. And then these are the clusters that Urania identified. They can shed some light about the input data set. It has keywords, also a description about what's going on in this cluster's size, and some histograms that can give you a different angle of what's going on in the cluster. For example, if it is chatbot AI conversations, then it can be distribution of tone inside this cluster. And let's take a look how Urania works under the hood. First of all, first step is extraction. We extract so-called facets. This is a structured metadata about the conversation or example, such as keywords or summary. And then we do clustering step. We cluster examples based on their summaries. And then we summarize the examples inside the cluster and generate cluster name and description that have differential privacy properties. Let's dive deeper into the first step. The first step is facet extraction, and the input here is raw unstructured data. For example, a conversation with AI, but it can have many modalities. For example, it can be audio or images. And then we spin up our own LLM where we prompt it with the conversation and ask a couple of questions. For example, give me keywords that describe this conversation or short summary about that. So this is kind of transformation of unstructured data into more structured format. And then we take summaries from the step one and embed them using semantic embedder, such as Gecko, for example. So we get n-dimensional vectors, which we can then cluster with differentially private clustering so that we get differentially private cluster centers that ensure that enough people contribute to each cluster, and it has also some noise addition to get differentially private privacy guarantees. And then we do the third step. We grouped the examples into clusters, and then in each cluster, examples have keywords. Then we can do differentially private partition selection on these keywords and count them in differentially private way. That way, we get safe keywords with relative weights. And what we do next, we actually, again, query Urania LM and asking it, here are the keywords with their relative weights. Could you come up with name and description of this cluster? And because keywords are differentially private, we get the name and description that is differentially private too. And from our experience, if you have enough keywords, such as 50, for example, you get good quality of name and description. And Urania is not just theoretical. We already apply it in practice. The first application is safety and abuse, where we can find malicious patterns and avoid exposing humans to harmful content. The second application is where we analyze how users use a product, and we can steer the roadmap, define which features we should implement next. And the third application is debugging agents, where we can analyze failure patterns that agents have. And this is, Urania helps here a lot because agents are exposed to multimodal logs, which are quite sensitive. And of course, the path towards productionalization was not that smooth. The first challenge we faced was scalability, because we have to process millions of examples. Some of them are very complex, for example, agentic trajectories logs. And if the input is quite simple, we use Gemini Flash for speed, and Gemini Pro if examples are pretty complex, such as agentic trajectories. And to do that at scale and fast, we do it in distributed manner using Apache Beam. We self-host our workers with TPUs and self-host LLMs there, so that we can process millions of examples in less than a day and generate Urania insights. And actually, the second challenge was data itself. First of all, pre-processing is crucial, and it has to be good. If we deal with simple, plain chatbot conversations, then maybe we can just give it as it is to Urania. However, if we deal with complex agentic logs, they are messy and noisy. First, you have to clean them up so that they contain information that is crucial for your analysis. Also, context depth, if you deal with short snippets such as queries in some search engine, then they are quite short and lack some context. For example, fine for parking can mean different things depending on the context. And also, when we get just keywords, some information might be missing. For example, if we have keywords English and Chinese, it can mean both things, translation from Chinese to English and vice versa. Having more keywords will help here. And also, in general, clustering is subjective. First of all, there is no one-size-fits-all clustering. Therefore, you have to keep in mind what is your purpose of analysis and adjust prompts for Urania LLM accordingly. For example, if you want to analyze failure patterns of an agent, you have to instruct Urania LLM to create summaries that talk about the root cause of the failure and not about the goal the user wanted to achieve. Otherwise, you will cluster embeddings based on the usage and not on the failure pattern. And also, you have to balance between high granularity and overly generic clusters. We err on the side of high granularity and then do hierarchical clustering to merge similar clusters together, because otherwise in Web UI, our data analysts will see like 100 of clusters that look very similar, which is hard to comprehend. And of course, once you ran Urania, you would like to assess whether the results are of good quality. First of all, you can go to this web UI and manually assess. This is quite straightforward, but also very, very useful. And then we also have LLM-based autorator, which can evaluate a few metrics about how good clustering is. LLM-based here means that actually it underneath uses LLM again, querying it with cluster descriptions and few examples from this cluster, and trying to assess whether these examples really belong to this description. And the third option is also to generate differentially private synthetic examples, which can shed some light on and give better sense for data analysts what's going on in this cluster. I would like to wrap up with future directions we're going to take here. First of all, we will focus on continuous monitoring, which is very helpful when we, for example, deal with failure patterns, because we want to implement a fix and then track over time that indeed the number of examples in this cluster goes down. And the challenge here is that basically you want to be clustering to be stable over time, but also you want to see new patterns. Therefore, it has not to be frozen completely. And also reports generation, the thing we would like to create, because this web UI is good, but sometimes it's hard still to comprehend. A one-pager that would just highlight key findings and something unusual found there will help a lot for data analysts. And also differentially private synthetic query examples that I talked about, they really give a good sense of what's going on in the cluster and really useful for data analysts. Thank you very much for your attention.